Hello everyone, and welcome back to AI Navigator. Today we have an exciting and in-depth topic to explore. Demystifying deep learning, exploring neural networks, and real-world applications. Deep learning, neural networks, these terms might sound complex, but we're here to break them down for you and dive deep into their real-world applications. So make sure you are comfortable, because this video is going to be a quiet journey.
Let's embark on our journey by laying down the fundamental building blocks of deep learning. What exactly is deep learning, and why is it such a game changer in the world of AI and machine learning? Deep learning is a subfield of machine learning that aims to make machines mimic the way humans learn and make decisions. Think about it as teaching computers to think, perceive, and act like we do. Now, here's where it gets interesting. Instead of relying on conventional algorithms, deep learning leverages artificial neural networks that imitate the structure and function of the human brain. These neural networks are composed of interconnected nodes, known as neurons. Each neuron processes information and transmits it to the next layer. It's like a web of interconnected decision makers, each contributing a piece of the puzzle. The inspiration here is our very own biological brain. Just like in our minds, information is processed layer by layer. As we move through these layers, the network identifies patterns and makes decisions based on the data it receives. This is what makes deep learning so powerful and versatile. To truly understand the significance of deep learning, we need to delve into its historical context. Deep learning isn't a newfound concept. It's been around for several decades. However, it's garnered widespread attention and made significant strides in recent years, and here's why. Several factors have converged to make deep learning a game changer. First, the availability of massive data sets has given deep learning models a wealth of information to learn from. This means they can recognize patterns and make decisions with astonishing accuracy. Additionally, the use of powerful graphics processing units has enabled the rapid training of deep learning models. This computational muscle has allowed researchers and data scientists to tackle complex problems that were once considered out of reach. And let's not forget about the innovative network architectures that have been developed. These architectures, including convolutional neural networks for image recognition and recurrent neural networks for sequential data, have paved the way for remarkable achievements in fields like computer vision and natural language processing. Now that we've grasped the fundamental concept of deep learning and explored its historical evolution, it's time to delve even deeper into the heart of this fascinating field. In this segment, we'll take a deep dive into the inner workings of neural networks, breaking down their components and demystifying their functionality. At the heart of neural networks are layers of interconnected nodes, often referred to as neurons. These layers serve a crucial role in processing and transforming data. Let's delve deeper into the purpose of these layers and how they work together. Imagine a neural network as a stack of these layers, with each layer connected to the next. We have an input layer where data is introduced, one or more hidden layers that process information, and an output layer that produces the network's final decision. The input layer is the network's entry point, receiving raw data. The hidden layers are where the magic happens. They process the data and extract meaningful features. The output layer provides the final result, which could be a classification, a prediction, or any other decision the network is designed to make. To truly understand how neural networks work, we need to explore the critical concepts of activation functions and backpropagation. These elements play a fundamental role in the training process, enabling networks to learn and adapt. Think of activation functions as the secret sauce of neural networks. They add a level of complexity by introducing nonlinear transformations. This nonlinearity is vital because it allows the network to capture intricate relationships and patterns in the data. We'll explore some of the most popular activation functions, such as the sigmoid, rectified linear unit, and softmax, and discuss the scenarios in which each one shines. The sigmoid function, often used in the output layer of binary classification models, squashes input values into a range between 0 and 1. This is ideal for tasks where we're dealing with probabilities, like predicting the likelihood of an event. Rectified linear unit is a go-to choice for many hidden layers. It transforms all negative input values to 0 and leaves positive values unchanged. This simplicity makes it computationally efficient and helps networks converge faster during training. Softmax is often employed in the output layer for multi-class classification problems. It transforms the raw output into probability distributions, assigning probabilities to each class. This makes it a powerful choice when dealing with tasks involving multiple classes. Understanding activation functions is like deciphering the language of neural networks. These functions are the building blocks that enable networks to interpret and process data effectively. As we move forward, we'll unravel even more layers of the neural network, exploring their intricacies and practical applications. But training a neural network involves more than just activation functions. Backpropagation is the mechanism that fine-tunes the network's parameters, minimizing errors and enabling it to make more accurate predictions. Think of it as a continuous feedback loop where the network learns from its mistakes and adjusts its internal settings accordingly. Forward pass. The process begins with a forward pass, where input data is fed into the network, layer by layer, until it produces an output. Each layer performs a mathematical operation on the input data using the current set of weights and biases. The output from each layer becomes the input for the next layer. Error calculation. Once the output is generated, we compare it to the actual target values, revealing the errors or the differences between the predicted and actual outcomes. Backward pass. Now comes the crucial step, the backward pass, or backpropagation. The network uses the calculated errors to adjust its weights and biases in reverse order, from the output layer back to the input layer. This adjustment is guided by the chain rule of calculus, which allows the network to allocate responsibility for errors to each parameter. Gradient descent. The optimization algorithm, often gradient descent, is employed to determine how much and in which direction each weight and bias should be adjusted to minimize the errors. Weight and bias updates. The weights and biases are updated proportionally to their contribution to the errors. This iterative process is repeated for multiple iterations or epochs until the network converges to a state where errors are minimized. These are the engines driving the transformative power of deep learning. Stay with us as we move forward to explore real-world applications that harness the potential of these networks. Now, let's transition from theory to the tangible impact of deep learning. In this segment, we'll explore how deep learning is actively reshaping various industries, making a significant difference in the real world. One of the most promising domains where deep learning shines is healthcare. It's not an exaggeration to say that it's revolutionizing the way we approach medical diagnostics and patient care. Imagine a world where diseases can be detected at an early, treatable stage. Deep learning is making that vision a reality. By training neural networks on extensive medical data sets, we've seen remarkable advancements in early disease detection. From identifying cancer in medical images to predicting the risk of heart disease based on patient data, deep learning is enhancing diagnosis accuracy. Deep learning has revolutionized medical image analysis, significantly impacting the way we interpret complex visuals in the medical field. In the realm of medical diagnostics, deep learning has brought about a paradigm shift. Neural networks are now employed to analyze a variety of medical images, including X-rays, MRIs, and CT scans. One of the key strengths lies in their ability to detect abnormalities within these images. Deep learning models excel at recognizing subtle patterns and anomalies that might be challenging for the human eye to discern. But it doesn't stop at detection. These neural networks go beyond, providing detailed insights into the medical images. They can highlight specific regions, quantify measurements, and even predict potential outcomes based on the visual data. This technology isn't meant to replace medical professionals but to empower them. By assisting in the interpretation of medical images, deep learning becomes a valuable tool in the hands of healthcare providers, aiding them in making more informed and timely decisions. In essence, deep learning in medical image analysis is enhancing the precision and efficiency of diagnoses, ultimately contributing to better patient outcomes. The application of deep learning in autonomous vehicles is nothing short of revolutionary, shaping the future of transportation and safety. When it comes to self-driving cars, deep learning is the foundational technology driving innovation. Neural networks play a pivotal role in enabling these vehicles to navigate roads and make decisions in real time. Deep learning models within autonomous vehicles process vast amounts of sensor data, including information from cameras, LiDAR, radar, and more. These neural networks then make critical decisions, such as steering, braking, and acceleration, based on the analyzed data. One of the strengths of deep learning in this context is its ability to adapt in real time. The neural networks continuously learn from the dynamic environment, making them adept at handling diverse and unpredictable scenarios on the road. The ultimate goal is to enhance safety. Deep learning algorithms contribute to precise navigation, allowing vehicles to identify and respond to obstacles, pedestrians, and other vehicles with a level of accuracy that traditional systems find challenging to match. Deep learning serves as the intelligent backbone of autonomous vehicles, enabling them not just to drive but to navigate with a level of sophistication that holds immense promise for the future of transportation. Money matters, and the financial industry is not falling behind in harnessing the power of deep learning. Banks and financial institutions are increasingly relying on neural networks to streamline operations and mitigate risks. Let's explore how deep learning is making a substantial impact here. In the vast landscape of financial transactions, fraud is a persistent challenge. Deep learning models are a powerful tool in the fight against fraudulent activities. These models are trained to scrutinize massive volumes of transactions, identifying subtle patterns and anomalies that may signal fraudulent behavior. In the fast-paced world of finance, timing is often the key to success. Deep learning is transforming the landscape of algorithmic trading, where models analyze vast amounts of market data, identify trends, and execute high-frequency trading decisions. Let's demystify the technology behind two powerful applications of deep learning in natural language processing, chatbots and language translation. Chatbots are designed to engage in conversations that mimic human interactions. Deep learning models, particularly recurrent neural networks and more recently, transformers, form the backbone of chatbot technology. The process begins with the training of these models on vast datasets of human conversations. The model learns the patterns, nuances, and context of language during this training phase. When deployed, the chatbot processes user input using this learned knowledge to understand the intent and context of the conversation. Response generation involves the model predicting the next sequence of words based on the input it receives. The chatbot then generates responses that sound natural and contextually appropriate. With ongoing interactions, the model continuously refines its understanding, providing more accurate and relevant responses over time. Language translation powered by deep learning relies on neural machine translation models. These models, often based on transformer architectures, excel at capturing the intricate relationships between words and phrases in different languages. During training, the model learns to align words and phrases in one language with their counterparts in another language. It comprehends context, idioms, and linguistic nuances, making the translation more accurate and contextually relevant. When translating text, the model processes the input sentence and generates a translation in the target language. The result is a seamless, fluent translation that reflects the intent and meaning of the original text. Deep learning facilitates natural language understanding and generation. From chatbots engaging in human-like conversations to language translation services breaking down linguistic barriers. These applications showcase the incredible capabilities of deep learning in making our interactions with technology more natural and inclusive.
And there you have it, folks. We've just taken a wild ride through the universe of deep learning and neural networks. From the basics to the cool real-world stuff, we covered it all. Are you still with me? Good, because we're not done yet. If you're vibing with the tech talk and want more mind-blowing content, hit that like button and become part of our tech tribe by subscribing and slamming that notification bell. Got burning questions or just want to share your genius thoughts? The comment section is the place to be. Thanks for hanging out, tech enthusiasts. Until the next time, stay curious and keep rocking the tech world.